All right, rookie, grab your coffee, pull up a chair, and let's get into it. Welcome to today's Explainer, where I'm going to walk you through exactly how we handle advanced traffic filtering on the floor. I need to make sure you've got this down cold before I let you touch any of the live routers. You've totally mastered the basics, but out here in a real enterprise network, we need absolute precision. We're essentially acting as the bouncers for the entire network, deciding exactly which packets get to stroll right in and which ones get stopped cold at the door. So here is our game plan for today. We're covering 1. Graduating to extended ACLs. 2. The extended syntax breakdown. 3. Named ACLs and sequence numbers. 4. Tactical ACL placement. And finally, 5. Troubleshooting like a pro. All right, let's kick things off with Section 1. Graduating to extended ACLs and moving beyond the basics. Listen, you simply can't rely on standard ACLs when the boss comes over and asks you to block a very specific department from hitting a very specific server. Standard ACLs are, well, they're kind of blunt instruments. They only look at the source IP address of a packet, and that is literally it. Think about it. If you use a standard ACL to block Bob from the HR web server, you might accidentally block Bob from the entire network. Extended ACLs, though, they give us surgical precision. They let us match the exact protocol being used, like TCP or UDP, along with both the source and the destination IP addresses and even the specific port numbers. So we aren't just blocking Bob completely, we're just blocking Bob's web browser from hitting that HR server while still letting the guy check his email. Moving right along to Section 2, the extended syntax breakdown, where we actually write the rules. So how does this actually look when you're staring at the terminal? Well, what's really interesting here is the incredibly strict logic the router uses. For an extended access list statement to permit or deny a packet, that packet must hit every single one of these parameters perfectly. You define the protocol, say TCP, then you drop in the source IP and its wildcard mask, then the destination IP and its mask, and finally the port. If a packet matches the source and the destination, but, I don't know, it's using UDP instead of TCP, boom, it's not a match. The router just skips right along to the next rule in the list. And when you're defining those ports, you don't just have to use exact matches. Sure, you can use EQ for equal to, like EQ80 for standard web traffic. But you can also use these operators to block or permit entire ranges of traffic, which is super handy. You can use GT for greater than, LT for less than, or range to specify a starting and ending port. So if you suddenly need to block all high-numbered ephemeral ports, you could just say GT 49151. It just gives you this incredible flexibility on the fly. Okay, pay attention here because this is absolutely crucial. The implicit deny. You must always remember the invisible wall at the very bottom of every single access control list. If a packet comes in and the router checks it against line 10, no match. Line 20, no match. Line 30, no match. What does the router do? It drops the packet. It outright denies it. If you forget to add a permit IP any at the bottom of your rules when you actually intend to let other normal traffic through, you will accidentally lock legitimate traffic out of the network. It's totally a rite of passage. I made this exact mistake when I was in your shoes, and actually, I literally took down the whole sales floor. Not a fun day. All right, Section 3, named ACLs and sequence numbers, or how we edit on the fly. So how do we fix a typo without bringing down the whole network again? Back in the day, standard numbered ACLs were incredibly rigid. If you made a mistake on line 3 of a 20-line ACL, you had to negate the entire thing, wipe it out, and retype all 20 lines from scratch. It was awful. But modern Cisco iOS handles things so much better using named ACLs and sequence numbers. You just type show IP access lists to view your rules, and you'll see they're numbered by default, usually 10, 20, 30, and so on. If rule 20 is a bad rule, you just enter the ACL config mode, type no 20, and boom, it's gone. The rest of your rules stay perfectly intact. You can even insert a brand new rule exactly where you want it by typing, say, 15 before your new command. It's a lifesaver. Let's move to Section 4, tactical ACL placement. Exactly where to drop the filter. Location is quite literally everything. An amazingly crafted ACL placed on the wrong interface or applied in the wrong direction does absolutely nothing for us. Let's play out a scenario on a typical corporate network topology. Imagine we've got a router right in the middle. At the top, an HR web server sitting at 192.168.1.4. Down at the bottom, a subnet full of our generic workers. If our strict security policy says we need to block those generic workers from accessing the HR server, but we still need to allow them out to the internet, where do we actually put the filter? Well, we create an extended ACL denying traffic from the generic workers subnet to that specific HR server IP. and permitting everything else. Then we apply it inbound on Ethernet 0/2. Why there? Because that's the interface directly facing the generic workers. We catch the bad traffic the exact moment it tries to enter the router. Which brings us to a massive golden rule of network engineering. We place extended ACLs as close to the source of the traffic as possible. Because an extended ACL specifies the exact destination, we know with certainty that it's safe to drop the bad packet immediately. This saves our network bandwidth because we aren't forwarding a doomed packet across 5 different WAN links just to drop it at the very end. Conversely, we place standard ACLs as close to the destination as possible. Because standard ACLs only look at the source IP, if you put one near the source, you'll accidentally drop traffic headed for perfectly valid targets. And finally, Section 5, troubleshooting like a pro, finding that invisible wall. So what do you do when the users are screaming that the network is down, but you look up and all your interface links are glowing green? Picture this. A user calls up in a panic. They can reach an internal company website just fine, but when they try to ping the server, it times out. So naturally they think the network is completely broken. Listen, this is incredibly common. End-user web traffic might be working perfectly while your ping or traceroute commands fail. Why? Because an access control list somewhere in the path is specifically configured to permit TCP port 80 or 443 for web traffic, but it is implicitly or explicitly denying ICMP traffic, which, as you know, is the protocol that ping actually uses. The network isn't down at all. The ACL is just doing exactly what we told it to do. So when you're stuck and packets just aren't flowing, I want you to run through this mental checklist. First, check for misordered statements. Remember, routers use first match logic. They read the list top to bottom, and the very first rule that matches a packet gets executed. If you have a super broad rule at the top that denies all traffic, and a really specific rule below it that permits the HR server, well, that permit rule will literally never, ever get hit. Always, always put your most specific statements at the top. Next, verify you didn't accidentally reverse your source and destination IPs. Trust me, it happens to the best of us. And finally, trace the packet's path mentally. Did you accidentally apply your inbound ACL to the outbound direction on the interface? All right, you've got the tools, you understand the logic, and you know the syntax. But I want to leave you with this final, critical thought to really chew on as you grow as a network engineer. As you master these extended ACLs to lock down our infrastructure, how will you ensure your rules don't accidentally cripple the business operations that were actually designed to protect? Security is totally essential for sure, but if the business can't communicate, well, then the network has failed anyway. Think hard about that balance as you hit the lab today. Thanks for joining me on this explainer, rookie. Now get out there and get your hands dirty on those routers.